All right, let us begin. This is our last live lecture. We're going to be reviewing for the final. And ideally, you've already started doing that. And so we want to get some practice questions and remind you of all those resources that you have to help you prep for the final. I went over a number of them last time, but we'll rehash those and also show you some other stuff. All right, so let's, and of course, for those coming to the final on campus, notice a different time, different location, different atmosphere, because you'll be during the math block exam. So let me go ahead and close that. And let's get rid of that. And we probably don't need these little pictures anymore. And let's get over here to the website. And we go over to the external links, files from the live lectures. Now this is session 9, so I'll be using these documents. From session 8, we had those things. And remember the questions to ask yourself. Keep practicing, because it's just a few questions you ask yourself and you know exactly which statistical method to be using for the given situation. Boy, that's a great skill to have when you're taking a final exam, so you know exactly the right thing to do for the given situation. To also make sure that you see how everything all fits together, let's get over here to the last learning module that has some nice gems for you. Getting over here to activities, want to make sure, if you haven't done so already, that you've made the little poster board, your own little poster board. And all you got to do is print out the documents. Well, not the first page. It gives you sort of an idea of the layout. But whichever one's in here that you find the most useful. I mean, this is a particular nice one for Chapter 4 for the regression. Seeing it all summarized in one page is less intimidating. So that's usually a popular one. If you have trouble keeping straight a population distribution versus a sampling distribution, this could be helpful. This might help you remember what a sampling distribution is. And hopefully you reviewed this one enough, but it wouldn't hurt to refresh your memory, keeping straight the differences here between quantitative and binary data. So you don't get those two confused with each other. And this is just helping you remember those few questions you ask yourself and you know what to be doing. And when the conditions are met. Same idea, notice it's basically the same questions for a confidence interval as it is for a hypothesis test. And know which sample size formula to use. There's some concepts from hypothesis tests, but this is probably the most popular one for hypothesis tests because that way you can see them all together and it's clear, you know, what each one is doing. Now, on the final, we won't have z-tests because that's rarely used in real life because you'll only use that if you know the population standard deviation. But all these others here, those are ones you want to know and know well. And notice that they all reuse these same concepts over and over again. Essentially, after you set it up, you use technology, and this is showing the function you use. That's the technology that gives you the p-value. Once you got the p-value, you use it the same way in all of these. So you know which hypothesis to go with. And you notice that you know what confidence interval to follow up with. You just replace the word test with either int or interval, and you got it. Now let's go ahead and set that one aside. And you'll notice here that you got a nice long list of practice final questions along with the solutions. These are the same ones that are on the tutorial DVD. In fact, let's just go over to the tutorial DVD. Practice exams and practice final questions. So those are also on here on your tutorial DVD, and they're also and right here in the last learning module. Okay, let's go ahead. We want to take a look at, oh, and of course you can see what your formula sheet looks like. This will be provided for you. All it is what the formulas you had on the first exam and what you had on the second exam. There's no more formulas after exam 2. We were just using our calculator to do the hypothesis test and follow it up with a confidence interval. And that's essentially it. Set that off to one side. Here's a document. This is a nice way to summarize what we've done in a very general way. Think of this as being able to list what your new superpowers are in dealing with data. But it also gives you an inkling of what you would learn if you continue on for a second term of statistics. Now, for some of you, that's inevitable. You know, business majors will continue on to business statistics. Psychology majors continue on to their applied psych stats. And biology majors will quite often take Math 244, which is only offered in the spring term, and I teach it. So you might consider maybe spring term, I offer an online version of it. I have a lecture class of it, and I have an online class. And I'm planning to use the same My Stat Lab. You wouldn't even have to buy another access code because it's the same book. And so it'd be like having a free book, free access code for spring term. And you would be continuing to use all the concepts you learned in this class. So we'll just think very generally, if you need information regarding some measurement for a huge population, and you'd like to know what the typical measurement is, that's the population mean. Well, you could do a hypothesis test, to test a claim someone made who thinks they know what it is. You can test that claim, follow up with a confidence interval to actually get an approximate idea of what it is equal to. And if that interval is too wide, you can determine how much bigger your sample size needs to be to get the confidence interval you'd be proud to have. That would have things narrowed down enough, and you would have the answer to your interesting question about the world, involving what the population mean is for a particular population of quantitative data. And of course, the same idea applied to categorical data with just 2 categories. By the way, if you would like to know how to work with categorical data that has 3 or more categories, well, that's what you would learn in a second term of statistics. Now, we also learned that you can compare 2 populations. And of course, that's what some call the bread and butter of inferential statistics, because we do so much of that. Because you're comparing 2 things and you want to know what's better, don't you? Well, if one of them is claiming to be better, you can test that claim with a hypothesis test. And if you find there is a difference, you'd like to know the magnitude of that difference, and that's what the confidence interval will tell you. And this would be if you're doing it with quantitative data, but same idea, you could do it here with the binary data. And could we use one variable to predict the other? To predict the future? Well, yes, that's what you learned in chapter 4 with regression. So, might want to look back at that because it's been a while since you've looked at it. So definitely you want to review your first midterm. Because just think you've already been tested on a lot of the material that's going to be on your final. So you've got what you did on your final. I sent you the answer key. So learn from any mistakes you made on your first exam. And then do the same thing with the second midterm. And then, of course, really review your hypothesis test. And, of course, if you were one of the good students who's reading the learning modules and you did the hypothesis test assignments that you sent to me and I gave you feedback on them. So learn from any mistakes that you made with that. Now, don't forget this stuff. This was back on your first exam. Remember how to make a box plot on your calculator. Don't want to forget that. And, of course, that that concept question number 1, how to apply it, which is what you did in the StatCrunch assignment. You know, you had looked at the shape and to see if there's any outliers, and that would determine what you're going to use to measure the center or the middle or the spread. And so that's a nice little summary of what you've done, what you can do now. And if you'd like to have more tools to your tool belt, well, because we knew how to compare 2 population means, well, what if you want to compare a number of them? The null says there's no difference. The alternative says no, at least one is. Well, you can just see, you just need to know which function to use on your calculator, and it'll give you a p-value, and you know how to use the p-value, and it'll tell you which one to use here. In other words, you're going to keep reusing the same concepts over and over again that you learned in this class. Hey, how about if you want to compare a bunch of population proportions all at once? And the alternative says at least one is different. Hey, just another function on your calculator. It'll give you the p-value, and you'll know which one to go with. Oh, by the way, this is known as analysis of variance, or it's called ANOVA for short. So that's why I say if you want to learn about this, then come on over to ANOVA. And let's see, there's the old goodness of fit test. Now, one that you see a lot that you would learn in the next one is the test for independence. It's similar to regression, where regression is for when both variables are quantitative data. Well, what if they're both categorical data? Well, that's when you would use this chi-square test, test for independence. Oh, and in chapter 4 of regression, you say, well, what value of R do I need to know I have a strong correlation or not? And we say, well, we really can't tell you, because it changes on your sample size, but you could do a hypothesis test. Remember the null would say there's no correlation. The alternative says, oh, yes, there is. Well, a function on your calculator will give you the p-value, and you know which one to go with. Oh, and in this class, we learned the first choice methods, the most powerful, most efficient, but the conditions have to be met. And the conditions aren't met, they're second choice methods. They're known as nonparametric statistics, and we cover that. Anyways, you just be able to add a whole bunch more tools to your statistical tool belt if you took Math 244. So, just keep it in mind, spring term. For those of you who got an A, get an A or a B in this class, you should consider it. If you got a C, well, anyone who gets a C in this class, they're missing some significant concepts, and they would have a harder time in the second term stats because of what they miss. All right, well, let's set that aside. Let's do some practice questions. So don't know what's coming next. They could be from the real beginning of the term, way at the end, or somewhere in between. So this is getting practice recognizing what statistical method to use. Well, let's look at this one. Can we predict population size by analyzing discarded garbage? Well, consider this. The following table lists weights in pounds of plastic discarded by a sample, well, let's say a random sample of 8 households, along with the sizes of the households. So here's the idea. We're going to take a random sample of households, and from each household, we're going to get 2 pieces of quantitative data. One of them is, we'll go and rummage through their garbage can and weigh the weight of the plastic garbage in there. And then we'll knock on the door with our grubby, dirty hands and see how many people live in that household. So as a measurement of the household size and the measurement of how many pounds of plastic garbage is in their waste bin, garbage can. So you've got this. And we want to find the equation of the least squares regression line. And then this work is all being done on your calculator, so hopefully you remember how to do this. And you'll get the value for an R and an R squared. So you can put those numbers down, but then say in words, what does that tell us? What does this one tell us? And you're being specific for what R and R squared, they each say in their own special way how strong the correlation is. And that's what you're explaining here. Hey, does this prove that the X variable is causing the Y variable to be what it is if it's a strong correlation? And then finally, would it be okay to plug in a value of 2 for X in our equation in order to predict Y, the household size? And how about plugging a value of 9 for X? Can we do that? All right. Well, the first thing we got to do is put this data in our calculator. But the big idea is what we're going to do here is, as it says right here, regression. So I'm going to put the X variable in list 1, Y variable in list 2, and I'll use my calculator to do the regression for me. So this is what you did back on exam 1. So let's turn this thing on. We'll press Stat, 1 for edit. And if I did have anything in the list, remember you highlight L1 and you press clear and then enter to clear the list. Well, let's go ahead and enter our data in. And I am going to double check, make sure I didn't do a data entry error. All right. Now, so how we run this is we press the Stat key, press the right arrow key to highlight Calc, because we got some calculating to do, and choice number 4 is the one I'll select. Oh, by the way, you know, you could do choice number 8, either 8 or 4 is good. Now, if I always put the X data in list 1 and I always put the Y data in list 2, then I could just hit enter. But if you use different lists, you would have to tell it. So for example, that'd be like L1, comma, second L2. But it's not necessary for me to put that in if I always put the X data list 1, Y data in list 2. It will just assume this. Oh no, I don't have the R and R squared. Hopefully you do, but if you're in the same boat as me, you're going to have to turn the diagnostic on because, you know, maybe you want to get ready for the finals. I'm going to put in some nice fresh batteries in my calculator. Well, sometimes when you do that, your calculator will reset itself and now the diagnostics are turned off. No big deal. Just press the second key and 0. Get you in the catalog. Press and hold the down arrow key so it starts scrolling. When you get to the D, start looking for something called Diagnostic On. There it is. Hit enter to select it and then hit enter again to run it. Now you'll get your R and R squared until you go and change the batteries again. So we'll press Stat. I'll go over to Calc. I'll do choice number 4, and this time I'm just going to hit enter. There you go. We're all set. So we got everything we need there. We just need to answer these questions over here. So let me do that. Get my little annotation tool here. Now, to get this equation, that would be y is equal to A, and A is 1.56. You know, if it doesn't say, just go out 2 decimal places. It's fine to go out more decimal places. Nothing wrong with doing that. And we'll put in our X plus B, so plus 0.27, rounding off. So that's the equation for the least squares regression line. If I want to predict y for a given value of x, I just put x, multiply it by 1.56 and add 0.27 to it. Now let's see our value for r. Now don't get this backwards. R is the 0.95. I'm going to go up 4 decimal places. 73. Now, R is not a percentage, so do not write it as a percentage. But R squared is a percentage, so it'd be okay to write it as a percentage, 91.65%. All right. Now, R is between -1, +1. The closer it is to 0, the worse the fit is, but the closer it is to either -1 or +1, the better it is. It's pretty close to +1, so that means this is a strong positive, so you want to see whether it's positive or negative, linear correlation. All right, well, that sums that up. Now the closer it is to 100%, the better it is. The closer it is to 0%, the worse it is. So this one's very intuitive. But what it's actually telling us is what proportion of the total variation in y that's being predicted by x. When I say total variation in y, I'm saying, look, when I go from one household to another, I never know how much plastic is going to be in there. Gee, some days it's just 1 pound, other days it could be as much as 5. And if you didn't know about being able to use this x variable to predict it, you're saying, I just don't know. It could be as low as 1, as high as 5. So the total variation is how much when it varies from 1 to 5. That's the total variation. So for us, 91.65%. So it's not explaining 100% of it, but boy, is it explaining a lot of the total variation and I should say in parentheses what y is, household size, is being predicted by x. Where x is the plastic garbage. And I would put that in parentheses here, but I kind of ran out of room here. All right, does this prove that our x variable is causing the y variable to be what it is? Doesn't that sound a little silly? As the dude, well, the husband goes out, looks in the garbage can, he says, honey, look at all this garbage in here. We're going to have some more kids. No, probably y is causing x. The more people living there, the more garbage you have. But we're not even going to say that. All we can say is that this is observational data, and you cannot use observational data to prove cause. If you want to prove cause, you would need to do a randomized, double-blind, controlled experiment. Well, you're not willing to go to that much trouble. Compared to that, this is easy. Just taking a random sample and observing what happens. So we'll say no. You can't use observational data to prove cause. That one variable is causing the other. Another way to say this is there's 3 explanations for a strong correlation. One could be x is causing y, but it could also be y is causing x, which would be believable in this case. But also consider there's probably some lurking variables causing these X and Y variables to be what they are. And just by happenstance, these X and Y variables are correlated with each other, which is great because then I can use my X variable to predict Y, and I'm not worried at all about cause. I just want to predict the future. All right, so let's go. Now, let's talk about what is the scope of the model. In other words, what's the limitation? Well, look at the range of values you observed for your X values. So let's find the smallest and the largest. So what was the least amount of garbage we found in here? Well, that is a 0.27 pound, a little over a quarter of a pound. And what was the trashiest place we found? Oh, this one, 3.05 pounds of plastic, discarded garbage. Now, we can plug in values for X, but we got to use X values that are between 0.27 and 3.05. And that's because this is all we observed. We did not observe any homes with less than this garbage or more than 3.05. And our really strong positive linear correlation, we can't expect that to go on forever. We know it definitely does within the scope of our model here, but it could change drastically beyond what we observe. It's known as extrapolation, assuming the linear relationship continues, and don't you do it. So, is 2 inside our interval? Yes. So 2 would be fine because it's within the scope of the model. How about 9? Did we observe any houses that trashy with that much garbage? Not by a long shot. That's way outside the scope of our model. So 9 would not be fine. Or okay. It's beyond the scope of the model. Okay, now one of these not covered in this one, but do you remember how we verified that the conditions were met for this number one choice statistical method? It was a little different here because what we had was a tool. It was called the residual plot. So imagine looking at your scatter plot, tipping that regression line over so it's horizontal, and then exaggerating or zooming in on the residuals to see how all those points are clustered around the regression line. And what you're hoping to see is constant error variance with no discernible pattern. And if that's the case, the conditions are met for this method. And if those conditions aren't met, well, if you saw a discernible pattern, what you would need is to learn nonlinear regression, which you would learn in your second term of statistics. Oh, and if it lacked constant error variance, you'd have to use a second choice method, one of those nonparametric methods. Not as powerful, not as efficient, but still pretty good. All right, let's clear all this. And let's just take a scroll down here so you can see all the prettier work being done. You notice here that after X, I clarified what that was, along with what Y was. And here, I explained, why it was okay for 2 and for 9, why it was not okay. All right, well, let's take a look at another one. Remember, we don't know what's coming next. Could be anything. Okay, so the Nielsen Media Research wants to estimate the mean amount of time in hours that full-time college students spend watching television each weekday. So And find the sample size necessary to estimate the population mean with a 0.25 hour margin of error. And maybe with television, now that would have nowadays would have to include Netflix, TV shows. We want a 95% confidence level, and the population standard deviation is known to be 1.87. All right. So what are we supposed to do here? What words answered my first question? What are they asking for? Well, find the sample size necessary is telling you it's a sample size problem. So if you go to your formula sheet, you'll see there's 3 sample size formulas. And of course, you also have this handy little table here. So let's see. Now, the one with the standard deviation, that's the one that's for the quantitative data. The other 2 are for the binary data. When you have binary data, either you have a p-hat or you don't have a p-hat. So what kind of data do we have here? Well, we're measuring how much time they're spending watching these TV shows. So that's a measurement, and that is quantitative data. All right, so only one of these is for quantitative data, and it's the one that has a standard deviation. So this is our formula. You only had to ask yourself 2 questions. What were they asking for a sample size? What type of data? Quantitative, and that told you it was this formula. And all we got to do is plug the numbers in, because they're telling me that with a 0.2 margin of error, E is 0.25. The standard deviation is 1.87. And if this is 95%, I just go down to my table. So that critical value, Z, is 1.9600. And that goes in right there. Well, that's not so hard, is it? Now, always have to show your work. So you write the formula out, then with the numbers substituted in, and then you punch it into your calculator. So there's your formula, and all the numbers substituted in that they gave you. Now let's go over to our calculator. See if we can punch that in after I clear this out. There we go. So I got 1.9600 multiplied by 1.87 divided by 0.25, right parenthesis. Oh, and if I forgot to square it, does that look like a reasonable answer to you? No, it doesn't. So if you leave a answer that doesn't look reasonable, well, not only did you make a mistake, but you didn't even really think about your answer. You should know that that's not right. Now, if you look back at what you did up here, let's press second enter, bring it back. You see, oh, I see, I forgot to do the square. Now we're talking. So we knew it needed to be really big. Now we know how big. Now, even if that was 214.1, we round up on sample size calculations, because we're saying our sample size has to be at least this big or bigger, and that means rounding up. So we're rounding up to the next whole number, which is 215. Now let's look at this one. Oh, I dug this out from the dustbin of history here. Byte Magazine, that's not around anymore. A reporter for Byte Magazine wanted to conduct a survey to estimate the true proportion of all college students who own personal computers. Well, you see, way back when Byte Magazine was around, not everybody had personal computers. Why, you were lucky if you had one. Sounds funny now, huh? Well, anyways, she wants 98% confidence that her results have a margin of error of 4%. How many college students must be surveyed? Now, for a more modern version of this, maybe you'd be trying to find out what proportion of this population as an Android phone or an iPhone or some other thing. But do you see how it's categorical data, qualitative? Now, either you're in this category or you're not. So binary data. And that's actually our second question, what type of data? What's the first question? What are they asking for? How many college students must be surveyed? Hey, that's how big the sample size needs to be. This is a sample size question. So it's going to be one of these formulas here. And we already answered what type of data is it. It's binary, so cross this one out. It's between these two. So the question is, do we have a p-hat or do we not have a p-hat? That's what determines it. Well, let's see. What did they give us? They gave us a confidence level, which I'll be able to look up down here. Well, that's swell. They gave me the margin of error E, so I got that. Did they give me anything else? No, they didn't. They didn't give us a p-hat. So cross that one out, and this is all we're left with. So E here is 4%, but you got to enter that in its decimal format. So if they give it to you as a percentage, take that number, divide it by 100, and that's what it will look like in decimal format. 0.04 is what I got to enter in there. And the confidence level is 98%, then the critical value is 2.3263. You just plug that in there and you calculate it. And your sample size needs to be at least that big, so you round up. Here's the work. So you can see there's the 4% in decimal format. There's the 3.263. Now let's punch our calculator and be careful. Only this part gets squared. Don't you square the whole thing or you'll get a wrong answer. 0.25, left parenthesis, 2.3263. And we're going to divide that by 0.04, right parenthesis, and then square it. And you round up and you have 846. Now, by the way, let me press second enter. Now, let's suppose you forgot to enter your margin of error E in decimal format. Now, sometimes they give it to you in decimal format, sometimes they don't, so you just got to be observant. But if you put 4 in there instead of what you were supposed to do, what kind of answer are you going to get? One that doesn't make sense. That's not a reasonable answer. So you should know you did something terribly wrong and look back at your work and see what it is. But if you give an answer like this, then it tends to imply that, well, you're not thinking about your answer. You're just looking at your calculator and copying down what it says and moving on, and you're not thinking. All right, let's see what the next one's about. So the students of the university randomly selected 217 student cars and found that they had ages with a mean of 7.89 years and a standard deviation of 3.67 years. And that's summarized right here. They also randomly selected 152 faculty cars and found that they had ages with a mean of 5.99 years and a standard deviation of 3.65 years. And that's summarized for you over here. Use a 5% significance level to test the claim that student cars are older than faculty cars. So, take a moment to look that over. Okay, so let's think about this. See, here's the questions that we ask ourselves. First, what are they asking for? They're asking us to test a claim. All right, it's a hypothesis test. So we got that. Next question, what type of data is this? Well, we're measuring how old the cars are. So that's quantitative data. All right, hypothesis test for quantitative data. Our next question is, do we have one sample or do we have two samples? It's one or the other, one or two. it won't be until your second term of stats that you have 3 or more samples. But just, I said, let me count. 1, 2. Hey, I got 2 samples. All right. So it's a hypothesis test for quantitative data with 2 samples. There's one last question, and you'll know what statistical method to use. Are these matched pairs? In other words, are these dependent samples? And if they're not, then they'll be independent samples. So either they're dependent matched pairs or they're independent samples. Now, if they're dependent samples, it's really just one random sample, and that one random sample determines what measurements are going to be in your 2 samples. See, the measurements in those 2 samples are dependent upon that one random sample. Or do we have 2 independent random samples? Because if you have 2 random samples, that's when you have independent samples. So what's happened here? Well, this was a random sample, and this was a random sample. So 2 random samples tells you they're independent samples. You know what else tells you? These aren't matched or paired up in any way. You know what else tells you? How could they be? They're different sample sizes. All right, so now you know. This is where we do 2 independent random samples hypothesis test. Oh, and then your calculator, if we go over to stat test, it's a job for 2 SAM-T tests. But we can't run that yet until we set up our hypotheses. First things first, So rather than scroll down, I want to show you the process, because this is one of the more newer things you've learned. So our null hypothesis is saying that the population mean for the student cars is the same as the population mean for the faculty cars. So group 1 is the student cars, so that population mean 1 would represent the typical age of the student cars. And population mean 2 would represent the typical age of the faculty cars. And what always goes in the null hypothesis? The equal sign. Because we're saying there's no difference between these. They're the same. Then our alternative hypothesis says, oh, yes, there is a difference. So copy down everything except for the equal sign, and then read carefully to see what it is they're interested in here. They want to know if the student cars, that's population mean ones, are older. So that quantitative measurement will be bigger because they're older. So that's what they want to know. And we're going to use a significance level of 5%. Now, would you like to be one of the students who really learn hypothesis tests really well? If so, then be sure and make this sketch, which is called If the Null Hypothesis is True, then the distribution of all the different test statistics we could get will be normally distributed, and in the center will be 0. Then 1, 2, 3, and it's a t distribution. 1, 2, 3. Now, with that 0, notice that this could be written as, well, if we subtract these 2 population means from each other and they're equal, what would that difference equal? 0. So that 0 difference is what this represents. Now, if we get a test statistic that lands close to the center here, let's suppose that it's bigger but only a little bit. Well, that's not unusual. That's exactly what I expect to happen if the null hypothesis were true. So if you land close to the center, you're going to go with the null hypothesis. But if you're far above, that's evidence supporting the alternative hypothesis. Because you see, if population mean is bigger, then you have a big number minus a smaller number. You're going to be off to the right here. So that's what we're going to find. Now remember, your p-value from wherever point you land, if I land close, well, the area to the right would be big, wouldn't it? Well, that's why a big p-value tells you you landed close, and if you land close, you're going to go with the null. But the farther away you are, well, you can visualize the area to the right getting smaller and smaller. And if you're so far away that the area to the right is 5% or less, well, that means you're far enough away to support the alternative hypothesis. Oh, yeah, and let's suppose I went with the alternative hypothesis. I could be wrong due to sampling error. What type of error would that be? Oh, I don't know. Type 1? Yep, type 1. And of course, if I land close, I'm going to go with the alternative, and I could be wrong due to sampling error, and that would be a type 2 error. So keep running those concepts through your head. Like whenever you set up a hypothesis, just run the whole process, the fundamental concepts through your head, because those are the concepts that are used over and over again in every hypothesis test you do. And for those going on for a second term, you'll continue to use them over and over again. So you might as well just learn them now. Why put it off? You kind of want to do well on the final, and if you want to learn more statistics, you got to know those fundamental concepts. Don't just memorize them by rote. Get the logic down. Well, you know what happens to students who says, oh, I'll just memorize. You know, if I have my p-value is bigger than the significance level, then I go with a null. And if it's smaller, I go with the alternative. You know what happens to those people on the final exam? Sometimes they forget which way it goes. And isn't that a heck of a note? Well, that's what you get. You know, if you get the logic down, it'll stay with you for life. Okay, well, we've got this set up now. Let's go ahead and punch it in our calculator. Oh, I got to wake up my calculator. Okay. Whoops. There we go. This does fall asleep on me. We'll go to 2 cent t-test. And I'm going to have to highlight stats, hit enter. Now let's put in our stuff. Let's see, that was 7.89. And this was 3.67. And this was 217. Oh, by the way, the conditions are met. Notice we got large sample sizes, at least 30, and they're 2 independent random samples. And I guess we should be assured that these are huge. It's a really big university, and so these the populations are more than 10 or 20 times bigger than the sample size. Now let's see. This is 5.99, and this is 3.65, and this is 152. And we want to go over here and select the greater than. So population mean 1, bigger than population mean 2, just like we have it here. And just ignore pool, leave it on no, highlight calculate, hit enter. Okay, now when you get this test statistic, put it in your sketch. Because what that does is it really makes you think about what just happened. Saying, that tells me I'm I'm almost 5 standard errors above the center here. I'm almost off the page. 3, 4, 5. That would be right about there. So imagine landing there. How unusual is that? Well, that would be the area from here off to the right. Because this little tiny area is my p-value. And the p-value tells me the probability of getting a test statistic this far above or farther if the null hypothesis is true. So this is so small, you've got scientific notation. See the e to the minus 7? So this would be 7.2 times 10 raised to the negative 7 power. Really, really small. But you know what? If you always plot this on your sketch, you'll never be surprised by scientific notation. And your answer will make sense. You say, well, of course it's so small. Look how unusual that is. You're not at all surprised. Now, your test statistic is 4.91 standard errors above the center, the hypothesized value. Difference is 0. And your p-value, oh yes, and for p-value, don't use the little letter p. It's 7.2 times 10 to the negative 7. So our p-value, this shows the reason for your conclusion, why you're going to reject the null hypothesis and accept the alternative. Because there is sufficient evidence at the 5% significance level to support the claim that student cars are older than faculty cars. You see how I just stole the words right from right here? And after I wrote the short version, then I can show off stated in context. And whenever it's this conclusion, it always starts off with, there is sufficient evidence at whatever confidence level they gave you to support the claim, and then you can just steal the words. See, isn't that easy? Here, let me clear this, scroll down so you can see the prettier version. However, this is missing the nice sketch. But you also want to document, which function you use. So that way, if something goes awry because you entered something in wrong, at least I know you can correctly identify the correct statistical method. But if you don't do that, I'm wondering, gee, I wonder what they were doing. What did they use? I wonder if that's why they got it wrong. So the more you document, the more partial credit you can get if things go awry. And here you can see in words, stating it in context. But don't stay in context until you've done the short version. Because what happens is some students, they know how to state this correctly. They know the correct conclusion, but they'll often sometimes bungle this up. And if you don't show this version and all you have is this bungled up version, I'm not even sure whether or not you know the correct conclusion or not. So don't do that to yourself. So now let's suppose that you know what the shape, center, and spread is for an entire population of quantitative data. Well, if you knew that, oh my gosh, think of the things you could find out. Now, maybe back when we were working with one populations and we're trying to get an approximate idea of what the population mean was, you realize that, hey, yeah, statistical methods could approximate the shape, center, and spread. And once I know those three things, this is what you learned in the middle of the class. Hey, I can find probabilities. Because in order to calculate a probability, you kind of need to know everything about the population, don't you? Now you might wonder, but wait a minute, we calculated this p-value, that's a probability. But remember, it's a probability that we can only do because we assumed the null hypothesis is true. And the p-value is based upon the null hypothesis being true. And that's how we were able to state a probability. I'm saying if the null hypothesis is true, then the probability of getting a test statistic as unusual as the one we found right here is, and then of course we state the probability, the 7.2 times 10 raised to the negative 7 power. All right, so now if 25 are randomly selected from this population that we know the shape, center, and spread, what's the probability that the sample mean from this random sample is less than 66 inches? Now think back. Remember that little template for distributions I showed you some weeks ago in a live lecture? They're asking you for find a probability. Your next question is, well, what type of data is it? Well, these are measurements, so it's quantitative. All right, it's a probability for quantitative data. I got one last question. Was one randomly selected or was more than one? It says the probability of one randomly selected being interval, that's a population distribution problem. But if it's more than one, it's a sampling distribution for the sample mean problem. Well, that's what this one is, more than one. And if you want to find the probability of the sample mean being in an interval, like less than 66 inches, you would need to know the shape, center, and spread of all the sample means. Oh, well, that's what a sampling distribution for the sample mean is. All right, so that's what you got to do. How do you know the shape of all the possible sample means is normal? Well, if you're sampling from a normal population, your resulting sampling distribution will be normal. All right, so that's covered. What would be the center? Well, all those sample means cluster around the population mean, so this would be the center. What's the spread? All right, if you're going to make a mistake, this is where it's going to happen. It's not the population standard deviation. That's the spread of the population distribution, not the sampling distribution. You got to use the standard error, which is this population standard deviation divided by the square root of the sample size. And it's right there on your formula sheet, right there. That's your standard error spread of all the sample means. All right, and then once you got that figured out, then you can use normal CDF to find your probability. So here's all the work being done, and the standard error calculates out to 0.58. Now, when you look at 0.58, don't think, hey, is that 58%? Well, you got to think about your answer. No, standard error is a measurement. So what units we're doing is an inch. So that's 0.58 inch. That's a little over half of an inch. Boy, those sample means are clustering in close around the population mean. So here's your nice little sketch. What would be really swell is if you had put this in and then use this right here to get the other numbers under the tick marks. Because I tend to give students a little green plus for that. And as you know, those green pluses add up for extra credit. Because now here's another thing you do. Well, where is this 66 on there? Well, let's do it this way. Let's turn that into a z-score. So if I do that, do a left parenthesis, so 66 is the sample mean. How far does that deviate from the center? Well, the center is 68.75. It's a subtractional find. And then we'll divide that by the spread. In other words, how many times does the 0.58 fit into that deviation? So that means this 66 is 4.74 standard errors below the mean. So on our sketch, we had to go 1, 2, 3, 4, and then 7. Oh, I'm almost off the page here. So we're going from this point off to the left. Well, that's pretty small area, isn't it? And you say, you know what? I'm expecting scientific notation if it's that small. So notice you could convert it into a z-score to locate it, or you could have taken this and found these numbers and you would realize, oh, 66 is way off to the left here. And so, but now here's your showing your work. 66 is the upper bound. It's going off to negative infinity. Now you don't have to use this, but go way off to the left though. Especially here, because this is already way off to the left, the 66. And you got to go even farther to the left. And of course, you've got your center and spread figured out here, so you just plug those in here for the center and spread. Now let's punch this in. Second vars. Whoops, let me try it again. Second bars. There we go. And we want normal CDF. Let's see, is 0 far enough to the left? Yes, it would. So I'll just do 0. Now, you know this negative 1e99 is always far enough to the left. But if you do a sketch with the numbers in, you know that all the other infinite number of values you could use. But you got to use 66 for the upper bound, comma, and then the 68.75, comma, and then our 0.58, our standard error. Right parenthesis, hit enter. Yep, that's pretty small, 1.06 times 10 to the negative 6. So that means this decimal point gets moved 6 places to the left. Very, very small. Because that's the proportion of all the possible sample means that will be less than 66. And that is the probability that the sample mean is less than 66. So that's what you did back in chapter 8.1. Let's look at this. The population mean has historically been 68.75 inches for this particular population. You want to test the claim that it is less than 68.75 inches now. Test a claim, huh? That sounds like a hypothesis test. You took a random sample of 25 and you got a sample mean of 66 inches. Based upon previous statistical methods, you have determined the population is approximately normal, and the population standard deviation is approximately 2.9 inches. And we're going to test the claim at a 5% significance level. Okay, so this is a hypothesis test. It's quantitative data, and it's one sample. So it's a one sample hypothesis test for the population. So you set up your hypotheses, and 68.75 is the hypothesized value. And let's get the sketch in here. So I'll do that. One, two, three. 1, 2, 3. And let's see, so I'll put an X bar here for the distribution of all the sample means. And this is what would happen if the null hypothesis is true. And if it's true, that all these sample means will be clustered around the 68.75. Right there in the center. Now our test statistic is this 4 by, so let's extend this out. 1, 2, 3, 4, 5. So it's probably right about there. So how unusual would it be to be this far below or farther? Well, that's this tiny little area. So that tiny little area is the p-value. And this right here is where the 66 was, our sample mean of 66. So what's the probability of getting a sample mean this extreme or more extreme if the null hypothesis is true? Well, that's this probability right here, the p-value. You say, boy, that number looks familiar. Even this test statistic looks familiar, doesn't it? Well, you just saw it on the previous problem, didn't you? Where I standardized my sample mean into a z-score. And this was using z-test. Now, rarely do you use z-test. And I only did this just so you could see that what we did previously, calculating how unusual the sample mean is essentially what you're doing with a p-value. So that was the point of that one. All right, let's clear our little drawing here. So remember these from did a bunch of these on exam number 2. Now, previously we were doing the probability of a sample mean being an interval. But notice here, we're given the shape, center, and spread of an entire population of quantitative data. And when you've been given that, you could find what proportion of this population being in a particular interval. You got a lower bound and an upper bound. So we're talking about a proportion of the population being an interval. Well, it's for a population, so this is a population distribution problem. Now, if 1 is randomly selected, what's the probability that 1 randomly selected is an interval? Well, if it's 1 randomly selected, it's a population distribution problem. Well, what if 25 are randomly selected? Well, if more than 1 is randomly selected, it's a sampling distribution for the sample mean problem, like what we were working with earlier. What is the percentile rank of one of these, of a data value being? Well, remember, percentile rank tells you the proportion of the population that is less than that data value. Well, you're talking about a proportion of the population. It's a population distribution problem. So that means for A, B, and D, you'll be using the population standard deviation of 2.9 inches for the spread. But for C, you're going to have to use the standard error, which would be the 2.9 divided by the square root of 25. Okay. So here you can see the work on those. So the first one, notice we're using 2.9, the population standard deviation. It's the proportion of all men are between 64 and 78 inches tall. And it's also the probability of 1 randomly selected man being between 64 and 78 inches tall. Now, the probability of 1 randomly selected being less than 67 inches. So anything way off to the left, 0 works, but you could use negative 1e99 if you want. This is the upper bound, because we're talking about less than to the left of 67. And this is your center and spread of your population distribution. And so that's the probability right there. Now for C, this is the sampling distribution, so you got to use the standard error. So notice we got the same interval, except this is for 1 randomly selected, and this is for the sample mean. Same lower bound, same upper bound, same center. It's the spread that's different. This is the standard deviation. This is the standard error. It results in a very different answer. Now, so notice that anytime you want to find the percentile rank for a given data value, just find the area to the left. And normal CDF will do that to you. The data value will always be the upper bound. Negative infinity will always be the lower bound. Just put in the center and spread for your population distribution and that area to the left. Oh, 15% of the population is below it, so it's at the 15th percentile, or percentile rank of 15. All right, okay, one last one, and then we're going to call it quits. The tobacco industry closely monitors all surveys that involve smoking. Well, of course they do. One survey showed that among 785 randomly selected subjects who completed 4 years of college, 144 smoked. So our population of interest is people who have completed 4 years of college. So we take a random sample from that, and from each, and as you go through that sample, what are you doing to each of them? Are you measuring something, or are you putting them into a category? One of 2 categories. Yeah, you're putting them into one of 2 categories. Okay. Because you're seeing whether they smoke or not. And so we counted 144 out of the 785 smoke. So construct a 95% confidence interval for the percentage of smokers among all people who completed 4 years of college. We want to get an approximate idea of what the population proportion is. And we're doing a confidence interval. All right, so What are they asking for? Confidence interval. What type of data is it? Binary. Do we have one sample or two samples? One. Okay, so it's a one sample hypothesis test for the population proportion. So going over here, oh, my calculator fell asleep again. So we go over to stat, test. Now I have to scroll down, getting these confidence intervals, and it's one prop z int. You can go in there. And so what was X? That was your count. Now, how many of your sample were in the category of interest? 144. How big was your sample size? 785. What confidence level do you want? 0.95. Highlight calculate, hit enter. So we're 95% confident that the population proportion is, and let's just steal the words, population proportion of all smokers among people who have completed 4 years of college is somewhere between 15.637% and 21.051%. Oh, I wonder if the conditions are met. Well, notice that on your formula sheet, this little test, use that to see if your sample size is large enough. Got the random sample, that's good. Huge population, that's good. But is the sample size big enough? Well, your p hat is the 0.1834, and n, hey, let's just check it out right now. 785 times 0.1834 times 1 minus 0.1834. And does it pass? Well, it certainly does. All right, so the conditions are met. And I state in words, but you'd probably like to see that in writing. And I don't blame you. Oh, look. See how they went? They verified the conditions were met and they showed it. Why, I ought to give this person a green plus on the exam, don't you think? They deserve it. And so we got, here it is stated in words and in context. Okay? So definitely make sure you use that last learning module, remind you of the resources you have, reminding you, you got those practice exams, especially exam one. You haven't looked at exam one for so long. Why don't you do some of those extra practice exams going back to those earlier learning modules and do that and learn from any mistakes that you made on your first exam, and then do the same thing with your second midterm. And then review the hypothesis test and make that little poster board, summary poster board, and keep reviewing those concepts. And keep doing it every day this week and continue on until you take the final. Okay? And that daily review is what makes it sink in. So don't let a day go by without running it through your head, all those concepts. All right. And that's it for our live lectures.